Last week, we learned about an electric dipole. What is an electric dipole, children? Two equal but opposite charge separated by a short distance of 2a. This was called as the electric dipole. Now, there is a dipole moment which is acting on the dipole. Dipole moment P is calculated as one of the charge into the perpendicular distance. SI unit of charge is coulomb and SI unit of distance is meter. Ensure that it should be written as capital C and small m, and coulomb meter is the SI unit of dipole moment. And dimension is Q is equal to, dimension is AT and length is L. So this is the dimension of dipole moment. Then we learned that dipole moment is a vector quantity whose direction is from negative to positive. And in the last week, we derived an expression for E axial and E equatorial. So today, we need to learn dipole in uniform electric field. This is external electric field. Okay. And what do you mean by uniform field? Everywhere the field strength is same. And normally, parallel lines with arrow, this is called as the uniform field. This is uniform. We have learned it in magnetic field also. But if the field lines are not parallel, then we can say that this is a non-uniform field. You know that, suppose if I keep a charge Q here and a charge Q here, the electric field lines are crowded. So the field lines are crowded means field will be more. More the field, more will be the force exerted on this charge because F is equal to QE. What about the force here? Here also F is equal to QE, but electric field is of less strength. So we are not bothered about the non-uniform electric field now. First, we will keep it in uniform electric field. So let's see what will happen to a dipole when we place it in a uniform electric field. So I'll draw the diagram for uniform electric field. For example, we are going to keep a dipole in uniform electric field. Uniform electric field. Okay. So I will draw the uniform electric field first. This is the uniform electric field E. Parallel lines show that it is uniform. Now, what is the direction of our electric field? Is always from positive to negative. So I keep a dipole in this electric field. Okay. In this electric field, I am placing a dipole. This is my plus Q and this is my minus Q. And this dipole is placed at an angle theta. It's inclined at an angle theta with respect to electric field. We have learned that any charge, when it is placed in an electric field, will experience a force. How much is the force? F is equal to QE. Since F is a vector quantity, definitely there will be a direction also. Okay. So if it is positive, it will have the tendency to go to negative. So we will see that force on plus Q will be equal to QE along the direction of electric field. Along E. Why? Because this is positive and it will be always towards the negative. So you can draw the QE like this. What about the force on minus Q? This will be, again, the magnitude is the same, but opposite to electric field. That means it should be drawn opposite. This is QE. And always remember, the length should be the same. Length should be the same. Okay. So now we will see that whenever two equal and opposite forces are acting, what it will create, children? two equal and opposite forces will create a couple. And what is the effect of couple? Rotation. And rotational force is torque. So I can write torque is equal to, grade 11 we have learned, one of the force into perpendicular distance. So now let's see the perpendicular distance from the diagram. So first we will write one of the force is QE into perpendicular distance means we need to drop a perpendicular from the first charge and from the second charge, and this is your perpendicular distance x. By geometry, we understand that if this is theta, this is also theta. So this is the dipole length 2a. So in this triangle, what is sine theta? Sine theta is equal to opposite side divided by hypotenuse, which is 2a. So what is the perpendicular distance now? 2a sine theta. And I can place it here. QE is equal to 2a sine theta. Okay. So basically we are getting the torque as QE into 2a sine theta. And we know that Q into 2a, we have already learned Q2a is P. So we'll get torque is equal to PE sine theta. So first of all, we will see when will this torque be maximum. Torque is maximum when theta is 90 degree and theta 90 degree. So this is the most unstable position of the dipole. And when tau is minimum, when the force is minimum, that means theta is equal to 0. So all the dipole will rotate and come parallel to the electric field. Now the significance of why it should be uniform. If it is not uniform, these two forces will not be equal. In one place, if the field is more, that force will be greater. So remember, a dipole, if it is not in a uniform electric field, apart from rotation, it will have translatory motion also. Now, from this formula, we can define what is the dipole moment. So what is dipole moment? Dipole moment is the torque. Dipole moment is the torque acting on a dipole. It is the torque acting on a dipole. Okay. That means tau will be equal to P, or P will be equal to tau when this is 1 and sine theta is 1. So if it is sine theta 1 means theta should be 90 degree. So acting on a dipole, when placed, dipole should be placed perpendicular to uniform. It should be very clear that it should be uniform electric field of, what should be the value? Of unit intensity. So don't forget, dipole moment is the torque acting on a dipole when placed perpendicular to uniform field of unit intensity. So this is the expression for dipole moment. Okay. So these are the total concepts we have covered. Now only one more electric quantity is left in this chapter. Electric charge is over. Electric force is over. Electric field is over. Electric dipole is over. Now next week we will focus on electric flux. And we will learn a new law called Gauss's law. And 3 application of that. With that, first chapter will be completed.